right? Yeah, so I'm going to tell you a bit about the visit, maybe not now, maybe in the next lecture or so, when we have the quiz, so we'll have more free time. Right, need to spotlight. The new one. Yeah, they are ready. So everything before already posted in my college, right? Everything before you already have it. For today, I didn't post it intentionally because there are a lot of questions I'm going to take together. I don't want you to reveal it from the slides. So after the lecture, I'm going to post them, okay? Yeah, but we spent like 4 lectures on that slide. So that's the one we already covered during the last lecture, last 2 lectures, last 3 lectures, and so on. But I already split it, so we are going to post exactly what we cover in every lecture. We have a lot of things going on in the group these days. So if I miss anything, please remind me right away, okay? But as usual, we will have the office hour right after the lecture, as usual. I receive a lot of nice questions. Whenever you feel you're not sure, you're lazy to come to my office, just stop me at the end of the lecture. Let's discuss whatever you have, okay? All right, so good morning, everyone. Let's make sure it's recording. Okay. I'm not sure why I cannot spotlight the other camera, but we'll do it later on. Normally, I assign that camera as main camera, but we will see. All right, guys. So we'll continue today for the second chapter in the book. This is another important chapter. All of them are extremely important, including the number system. So nothing in this course is side topic or something that's not really important. Okay, so please take care of every single detail that we might cover. So again, we're on chapter 2 now. We are still in logic gates, okay, in the digital circuit. So we move from the data to the hardware right away. And we ask ourselves, okay, we represent any input as a number. We now very good in binary, hexadecimal, decimal, whatever system that we invent for the number, but then how we perform operation. And for today, it will be a very nice topic. So hopefully we'll cover that in detail. Okay, so we discussed last time if we want to represent any circuit to make it an abstract view of that circuit, we normally represent it as a block. And you'll see this very often in all NVIDIA paper, Intel, AMD, all of them. Whenever you open a data sheet, you'll see this block, okay? And what tells you, okay, I designed for you a chip, and here what you have in the chip. So you have what we call as a pin surrounding this block. Those are pins. And whenever we see those pins, it means I/O. I/O is an acronym for input-output. Excellent. Okay, so those are normally I/Os. The input, we have it to the left side, okay, because it makes sense. We start always English from left to right. So we start with input, and then we get the output, not the opposite. And then to the right side, we get the outputs. And with an inside, either we have the functional specification and the timing specification, or normally the functional specification would be there. Okay, the timing would be somewhere else, normally in a table. It will tell you the delay is this, the propagation delay of that circuit, of those wire, the resistance, the voltage, the amplitude, and all these details. But normally we have the functional specification at least over there. We could have this if the circuit is simplified or small circuit. Then we could have in-depth details about the circuit. So in this case, we have 3 black boxes. We don't know what's inside them, just whatever it's doing there. And then we have the input also to the circuit, and that's the output. So always to the left side is the input, the right side, the output. And if it is simple logic gates, then you will get those gates inside those blocks. Okay? And normally we said for simplicity, those normally not given, but for simplicity, we should assign a name to those internal signals. Okay? All right. Now we divide all existing circuits into 2 types. Combinational logic, okay, which we call them memoryless because we don't keep the bits or the value within the circuit. Okay, whatever the input, we get the output. Once we disconnect the input, done. There is no output. The other type of circuit, sequential. Okay, sequential. If there is no input or we disconnect the input, we still get the value because we keep some of the values within the device itself. Okay, and most of the logic gates belongs to this, or almost all of them, including the buffer. Okay. All right, let's start with combinational. Whenever we see logic gates, pure logic gates, that's directly combinational. So all elements must be combinational in order to call it combinational. Okay, if there is anything else or mix of elements, then it's no longer combinational. Okay, because the idea behind it is not to be able to memorize any value. If any of those elements is able to memorize or save some of the values, then it's no longer combinational. Okay, that's contradict with the definition of it. And this is extremely important. If we do it, we will violate the principle of those logic elements. Okay, so we should not have any of the wires or the node. The node means those legs, basically those pins. Okay, cannot. It should be either an input, like in those cases to the left side, all of those, this as well is input, or connected to exactly one output. And we discussed this last time, right? What does it mean? Connected exactly to an output. So this is an output. If you look at the left side, from here it's input, but from here it's output, right? So this one we cannot connect it to another output, okay? Because that will contradict the value. If some, this is, okay, let's have NAND. We cannot connect these two together because this could be 0, this could be 1. Which value should be the wire? That contradicts what we have, okay? So either this can be connected to unlimited number of inputs. So we have like 5, 4, 6, 7, and we got a lot of great questions last time. How many of them? Do we have a limit on that? Ideally, this is what we are dealing with here, ideal scenario, so we don't have any limit, okay? So we can connect it to unlimited number of input, as in here, or exactly one output, which is this guy, okay? So this one is wrong. You should delete that. The circuit contains no cyclic path. What does it mean? No feedback. Yes, please. Yes, of course, which is a resistance. We discussed last time 2 scenarios for real world problems. The first thing, the resistance. Whatever physical component you connect, including wires, all have resistance, including logic gates as well. The logic gates has its own resistance, okay? And whenever we have a resistance, we are impeding the voltage. We are degrading that voltage, right? By degrading the voltage, we could drop it from 5 to 2 to 1. And this is causing a problem because we are flipping the values from 1 to 0, okay? So whatever this can accommodate as a loss in the voltage, we can keep adding more wires. But normally wires is extremely little resistance, so it will not cause a problem unless the wires are really thick or the temperature of the circuit getting high, then all of that is going to push the limit for the resistance. Get it? Perfect. No cyclic path, never connect something from here to here. Never do that, okay? I saw all type of mistakes in the assignments. This is an example. Let's go now with the most important topic for today. Something we call it Boolean equation. Does anyone know what does it mean? True or false? Yeah, the result would be true or false, but not the equation itself. Boolean equation. Okay. It represents a functional specification of outputs in terms of input, which basically an equation, as it says, right? It's Boolean equation. Boolean means true or false. Yeah, that's correct. But at the end of the day, it's an equation representing the circuit. You don't care about the complexity of the circuit. Once you have that equation done, that will substitute the entire circuit. So it's a functional specification, means it's representing the functionality of the circuit, okay? Of output, so we should always have the output in one side in terms of the inputs, okay? So we start with the output. This is a combinational logic. CL stands for combinational logic, okay? Regardless whatever we have inside, this is the input. These are the output. So we always have the first output over here, and then we represent it as a function of input, function of A, B, C, N, okay? Likewise with the carry out or the C out, okay? We have it in one side, and then function of input. Now, to know the functionality of it, we should replace all of that with the actual functionality or the actual logic gates that we are using to make this function, okay? So in this case, can anyone tell me what it's doing? What is this? OR, XOR? Flipping? Is it OR? Oh, wow. You got all types of logic gates. And? No, this is XOR. Okay? This is XOR. So normally, the OR is plus, the AND is dot, and this XOR. If you want an AND, you put the dot like this, A, B, and then we have something like that, okay, to negate the entire thing. Likewise with the OR, A plus B, it means A or B. And then if you want it NOR, you negate everything, okay? Good? All right, so this is doing XOR, A XOR B XOR C. It means a single XOR gate with 3 inputs. Single XOR gate with 3 inputs. But you could still represent it as 2 XOR gate with 2 inputs. How? We take the first 2. This is the XOR. You still remember how we draw it? This is XOR, right? Now, we take the first 2, A and B. The output would be A XOR B. We take it to another XOR. And then we have CN. And that would be your output, not this one, okay? But this is intermediate signal, just we use it internally. And the output would be S. This is how we use 2 input XOR gates, okay? We need 2 of them. But we could represent it using 3 input XOR gate, something like that. So 3, A, B, C, N, and then the S over there. Is it clear? We'll see this very often in the next few weeks. Yes? Excellent point. You'll see the complexity is less in terms of the circuit, and that's going to occupy maybe less size. We don't know until we know what's inside this, how many transistor is occupied. If this is 2 and 2 transistor, like that's 4 transistor, and this we could implement using 3, then of course we are winning in this case, okay? But we have to worry about many aspects. We cannot tell. For example, the power consumption. Is the power consumption higher with 2 circuit or with 1? For example, the size. Is the area size would be higher, occupying more silicon or more transistor with this or with this scenario, okay? And then the cost. Of course, always when you go to Home Depot, for example, one single solution, it's normally very expensive, much more expensive than 2 separate solutions, right? And sometimes the opposite depends on this solution, what you are looking for. So we have a lot of things here to worry about before we decide which is better. In here, we have another Boolean equation that's representing the output, the other output, in terms of the input. And you can see here, what does this mean? AB, it's not this, not this, not this. What could be? And who says NAND? Or XOR? Okay, this is a bit better than previous question. This is AND. Okay, this is AND. When we don't have the dot, it directly means AND. Okay, it cannot be OR. So AB means A multiplied by B. Okay, and then plus. Okay, A plus is OR. Excellent. And then A CN. CN from here, it's not the C out. So always we have here input. We cannot have the C out going there again. Okay. And then OR again, B times CN. Right? Okay. Now let's really dissect. Yes, please. Definitely, you can add yes, then you are implementing this, the two circuits. Then you can do parentheses, right? So you can add parentheses to B and C alone, or A and B alone, or A and C alone, okay? And continue, okay? That's a very good point. All right, now let's dissect this Boolean equation, try to understand what are those elements. So we already know these things. That's good. OR and XOR, right? Now, the first thing, when you saw anything, any character, and we have over there what we call a bar, then what we call it? Call it complement. What does it mean? What is the complement of 1? 0. What's the complement of 0? 1. Okay. So it's like 1 minus whatever value we have. But the complement of it. So we could represent it like that. Sometimes you'll see it somewhere, like online. Could represent it with a bar. Sometimes you'll see something like this. Okay, they are both the same thing. Especially in old books, you'll see this more often. But both of them exactly the same. We call it a bar. So a bar. This is how you should pronounce it. A bar. Okay. You could use it for whatever you want, but without the bar, it means without negation, without a bubble. Now, the second thing, we call it literal or literal, okay? So literal means those elements themselves, the A alone, A bar, B, B bar, and so on. Okay? Any of those, we call it literal, right? Now, implicant, what does it mean? This thing. So any term that has several literal with AND gate in them, we call them implicant. Okay, so just like A dot B dot C, for example, or A dot B, and we said you don't have to write the dot. Okay, so without the dot, it's already the same thing, the same meaning. So A, B, C, D, and maybe here bar, doesn't matter. So all of that called implicant, or a term. You can call it a term. Min term, this is extremely important. So pay attention, please, to this and the following. Min term, the minimum term, it's the AND of several literal. Okay, so this one we call it implicant, but now we also call it min term. Okay, so if I ask you to represent a circuit using min term, you should never have any of those and then plus sign. That's not min term. We should always have AND with the literal itself. So A, B, C, something like that. Okay. Now the max term is sum of literals, which is just replacing the dot with the plus. So A plus B plus C. We will see in next few slides how we represent any circuit using those min term and max term. Okay, please pay attention to that. Any questions so far? Yeah, I know this might be boring definition, but once we saw it in examples, all things will be more clear. All right. The first topic called sum of product. Sum of product. What does it mean? It means we have products, and then we add the sum of them. When we do the sum, maybe this is getting messy. So sum of product, sum of product. Remember the name. From the name itself, you could directly infer what does it mean. So we should have products. And what does product mean? And then we should have the sum of those. If this is A, B, and that is the product, right? We do multiplication over here. And this is, for example, A, B bar, and maybe C, D, maybe bar as well. Then sum of product would be AB plus A bar B plus C bar D. That is sum of product. Is it clear? So the name is telling you everything about it, right? So you never get confused about it. Just think about it. Sum of something to mean a summation of all those terms. All right, let's see now. We have a truth table. We don't care what is the functionality of that circuit. We don't care what is it, okay? And truth table, last time we said it's extremely easy. We have the input to one side, the output to the other side. So all of those are input. Even without telling you that those are the input, you should directly infer yourself that those are the input and this is the output. This is how we read the truth table, right? Now we said how we fill those input. They have different ways. It depends on your mindset, how you think about it, and so on. The easiest way, you go to the right-hand side, okay, which is B, and you start alternating between 0 and 1, 0, 1, 0, 1, 0, 1, 0, 1, okay? The next column over here, you alternate with 2 zeros, 2 ones, 2 zeros, 2 ones. The third column over here, 4 zeros, not 3 zeros, 4 zeros, 4 ones. So this is binary system, so we go with 1, 2, 4, 8, 16, and so on. So it doesn't matter how many input do we have. We always start alternating from here. Single 0, 1, 0, 1, 0, 1, 0, 1. Here, 2 zeros, 2 ones, 2 zeros, 2 ones, 4 zeros, 4 ones, 8 zeros, 16 zeros, and so on. This is my way, my own way of defining it. But if you want to know the reason why we do that, you should always start from 0. So if you combine all these bits together, whatever number of input we have, all of them combined should value to 0. And the last one should value to the maximum. All bits should be 1. And this is where to stop when you keep alternating. So you alternate here 0, 1, 0, 1, 0, 1. When should I stop? When all the rows, when all the columns, sorry, become 1, 1, 1, 1, 1, 1. You already arrived to the maximum. You cannot continue after that. You cannot add more rows, okay? And you can see here, 1, 1, then stop. With 3 columns, you probably need the double of that number. So here, 4 rows, you need 8 rows to complete it because you'll go with 4 zeros and then 4 ones, and that is 8 rows, okay? Try it yourself, please practice. The only way to understand all of this fully is to practice. I cannot further explain this, okay? Just to practice. Do 3 input truth table, 4 input, 5 input, doesn't matter. It's never complex. All right, that's for the input side. Now for the output, normally it's given to you. You don't have to invent the wheel, either as a description in the question or directly it's telling you this is the output. Or sometimes it will give you a logic gates and you need to try with the AND or XOR until you compute the output as we see in the last lecture. Last lecture, we already got an example with the propagation delay, right? We apply the truth table for AND, OR, and we saw the intermediate signals. So we always recommend when you build the truth table, you have the input over here, then some intermediate signals and some the output at the end. This is if the circuit is complex. It's not complex, you don't need that. You don't need the intermediate names, okay? All right. Let's follow some rules on how you perform sum of products on a truth table, okay? The first thing, all Boolean equation can be written in sum of product form. Any truth table, any problem, any circuit, you can still represent it using Boolean equation in a sum of product form, okay? There is no circuit that you cannot implement using this. That's the first thing. Each row has a min term. So each row in the truth table, okay? This is what we mean by a row. Each row in the truth table is represented by a min term. Do you still remember what's a min term? Multiplication, okay? Somewhere, these guys. A times B times C times D times whatever, this we call it min term. If there is a plus or, that's a max term. So each row should have its own min term, unique min term representing that row. A min term is a product of literal, and we already discussed that. Each min term is true for that row. So this is extremely important. This will make the whole difference between sum of product and, we will see next, a product of sum. A product of sum. So we have sum of product, and next we will see product of sum. And what makes the huge difference is that each min term is true for that row. Each min term is true for that row. So if we choose this to represent that row, then this, using those values as A and B, should be equal to true. So for example, can we represent A, B for this row? Excellent. 0 times 0 is 0, so it's not true. Then we cannot use it for this row. Because here, by definition, each min term is true, which means 1. So when we calculate that min term for the row should equal to 1. For example, to where we, yes, true is 1. The binary system, true 1, false is 0. And likewise, 0 is ground, and 1 is VDD, which is high voltage. Sorry? No. I think I'm okay, the min term is just an equation. It's like equation. So A times B, we should have this equal to true or 1. Okay? Now, 0 times 0, does it equal 1 or 0? 0, so it's not 1. So we cannot use it over here. No, forget about y. Okay. Forget about y. Okay? Now, let's try the second one. 0 and 1. 0, and hopefully everyone can see here. Okay, perfect. 0, 1, which is the second row. 0 times 1, 0. So we are not getting the min term for the second row. Third row, same thing. Right? Last one, 1, 1. Yeah, finally we got it. So A, B, only we can use it to represent that row. We will see now an easier way how we can calculate all those min term right away. Okay, we don't need to think about it even. Yes, please. Excellent. We will see a way now. Okay. Yeah. But remember, those min term are unique to each row. So we cannot use the same min term again. Okay, so each row will has its own min term. All right. Form function by ORing min terms. So once we know the min terms, once we calculate all of those for the truth table, then we can have the Boolean equation for that truth table by ORing min terms where output is 1. So now we calculate all min terms for all these rows, and whenever output is 1, so here and here, we take the min terms that we calculate only for this row and only for that row, and then we OR them. And that's your Boolean equation. So first step, you build the truth table. Second step, build all minterms, one minterm per row. We will see how we'll do it. And then whenever the output is 1, like here we have 2 cases only, then take the minterm for this, the minterm for that, and OR them. And that will be your Boolean equation. Good? Do we agree? Okay. Here's the minterm. The minterm is something that you can populate right away, same as you did with the input. You don't need to think about it twice. Okay? Same way as we did over here. Do you remember we alternate 0 to 1, 0 to 1, 0 to 1, 2 zeros, 2 ones, 4 zeros, 8 zeros, and so on, right? The minterm is something you can do exact same fashion. Okay? Which means whatever input you have, A, B, C, for example, then you directly populate A, B, C, A, B, C, A, B, C in all of them. And now you start with 2 bars or all input as bar. Why? Because all input here are zeros. So we want to negate that in order to convert the 0 into 1 so that the final result would be 1. If we have any of them 0 or all of them 0, we will never arrive to 1. So that's why we need to cancel out all 0 values. If A is 0, directly add a bar. That will cancel the zeros. In the first row, we have 2 zeros. So we need to cancel both of them. So we add a bar to A, a bar to B, and that's going to cancel the 2 zeros we are having. Okay? Probably the room's getting high temperature. That's why you are quiet and sleeping, right? I don't see the window. Cannot open them, right? We need a way to make you refresh. Okay. I don't have enough bars here. I think you deserve one, right? You deserve another one. Oh, sorry. This is a new type, so please try it and let me know. Yes, please. Guys.
You're going to use the columns for the rows that have a 1 and y column.
Yes.
Yeah, so it would just be constructing it of the minterms. It would be bar A and B plus BB.
Yeah, exactly. So in here, when you build the minterm, don't worry about the output. Just hide it, forget about it, okay? Go to the input. How many input do we have? In this example, 2 input, A and B only, right? So directly populate A, B, the first minterm, the second minterm, A, B, third A, B, last A, B. Just populate all the minterms in terms of product of input. If you have 3 input, A, B, C, then just add C, 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 and probably you need 4 more, right? Because you'll populate 4 zeros and then 4 ones for the last one, which is A. Okay, but in this case, we don't have the C's, so let's delete them. And now we want to cancel out the zeros. Whenever we have a 0, just add a bar. Where do we have a 0 in A? The first 2. Bar, bar. As easy as that. Where else we have zeros in the B? Bar, bar. Done. These are the minterms. Extremely easy. You don't need to think about it. Don't build the equation and so on. Those are the minterms. Can you compare? Did we do anything wrong? All correct. Got it? How many input we have? 2. Okay, populate all of them A, B, A, B. Remember, this is sum of product. So we need to build minterm as a product. So don't miss it with, don't never add plus over here. Because at the end of the day, it will not be sum of product. It will be sum of sum. Because we are going to sum these terms at the end. So remember, those should be product. That's what the name is telling us. All right, now we build the minterm. We pass the second step. The third step, now look at the output, which is y. Whenever we have 1, consider the minterm. Do we have 1 in the first midterm? No. This guy out. Do we have 1 in second row? Yes. This guy in. Do we have 1 in third row? This guy out. Do we have 1 in the last row? Look at the output, not the input. The output is y, right? So now we have an input, yes. We have 1, sorry. We have 1, yes. This is the third step. Now what's the last step? Add them. And this is how we will get sum of product, or just or them, or is sum. Okay, so then what's our Boolean equation? A bar B plus A B. And this is the output, should be to the left side. Don't add the output to the right side. Okay, the output to the left side. How do we know the output is given to you? Okay, so y equal A bar B plus AB. Now use this equation to verify the truth table. It should be true for all rows. Doesn't matter, it's 1 or 0, the output. Let's try it out for the things that we didn't consider. For example, the first row. The first row, remember, A is 0, B is 0. Okay? A is 0, it will be 1. B is 0, it remains 0. Plus A is 0 and B 0, so 0 times 0. 0 times 0, it's still 0. 0 times 1, still 0. And then y equals 0. Is it 0 in the y, the first row? Yes. Try it with all rows, doesn't matter. This now is representing my circuit. I don't need the truth table anymore. I can give this equation to any manufacturer, and I will tell them, can you design a circuit for me based on this Boolean equation? Done. Okay? So this is representing all the time the y I'm having over here. Any question? Any question? Yes, please. Can you raise your voice? I have noise here. To calculate y. This column, you mean, the truth table. How we calculate y. Yeah, that's a great question. As I said in the beginning, y, most of the time is given to you. Okay, you don't need to calculate it. But sometimes I will give you the logic circuit and or some stuff like that. And you need to follow, trace the input and recalculate the output every time. Okay, same as we did when we studied the propagation delay last time. You remember how we calculated? But we use it using time form, right? Now we calculate using truth table. All right, good. Remember how we calculate the input as well? How did we calculate the input, A and B over here? How did we calculate the input? Not you, Alex. I need to give more bars. Lately, I returning back home with more bars. I don't know why. Let's see. Yes? Who was saying something? Yeah, go ahead. Got it? No? Not yet? Okay. Let's do that again. How many input do we have? Invent your own circuit. How many input do you want? 3? Okay. So let's give it a name. X, Y, Z. Okay? X, Y, Z. And remember, the left side is for input. Don't mix it up. Don't have the output first, then the input. Now, we go to the right side, the first LSB column, least significant bit, okay? And then we alternate 0, 1, 0, 1. I don't know how many rows I should continue. Okay, so I start with this randomly. Now, in the next one, I'll start with 2 zeros. You see 2 zeros. And then 2 ones. And keep continue, 2 zeros, 2 ones. Until when should I stop? I don't know yet. I'll go to the last row. Now, how many zeros? We are following the binary system. Binary system, 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, and so on. Continue with that. What is this? 1. What is this? 2. What is this? 4. What is this? 8. What is this? 16, and so on. 32, 64, 128, and so on. Okay? Those are the number of zeros that I should alternate with. So the first column with single zero only, second column with 2 zeros, third column with 4 zeros, not 3 zeros. Okay? So here, 4 zeros. 1, 2, 3, 4. Oh, I didn't alternate with ones. It means I cannot stop here. I should continue. 1, 2, 3, 4. That's for ones. Four ones, 4 zeros, right? Okay, I'm missing something over here. Let's continue. Here, 2 zeros, 2 ones. Here, 0, 1, 0, 1. Oh, I've arrived to a row that has all ones. Means you need to stop. You cannot continue, because this is the maximum value in binary that you reach out. Here, if you want to know that what you did is correct, you should value the entire row to 0. You should value the entire row. Maybe you can use another color, maybe red. So this is should value to 0. 1, 2, 3, 4, 5, 6, 7. This is, should be the value of the row. If this is not matching, it means you did something wrong. Let's try it out. This row, 1, 1, 0. Is it value to 3 or not? This is 1 and 2 together, value to 3, correct. This one, 1, 1, 1, 1, 2, 4. 4 plus 2 plus 1 is 7. Correct or not? Correct. And you already built the input in the correct way. Yes. Yeah. Yeah, we call it truth table, because it's telling you the truth, hopefully. If you do a mistake, then it's no longer truth table. Right? Okay, to the right side, we always add a vertical bar. Feel free to add it between the inputs, but it doesn't make sense because you need to value these together. So it will confuse you once you add bars over here. So don't do it. Just add the input and then the vertical line and then the out. Don't add too much vertical lines because it will confuse you with the ones. You have 1 and then vertical line, it might be interpreted as 1 and so on. And try to always make them aligned, make them vertically, all of them aligned. If you go shift to right or left, then you will make all mistakes. Good? Excellent. Are you sure? Okay, I'm going to check your grade in the assignment. Any question on this? Please stop me, whatever you want. I can delay the lecture. Doesn't matter how much content we cover today. I want you all to understand it. Yes, please.
Yes.
Yeah, 0, 0, based on the input. We didn't calculate it ourselves. We take it from the input here. A says 0, B says 0, right? So we just replace B with 0, A with 0. It's likewise here, B with 0, but here A bar, it's not A. So we have to flip the value. So it was 0 in the table. We flip it into 1. So 1 times 0 plus 0 times 0. Good? Just replace value. We didn't invent anything here. We are trying if our equation is matching what we calculate over here or not. Yes, Drew. Have a question?
No, figure it out.
Okay. Again, this is my own way of calculating the truth table. You might find many different ways. It's up to you to follow whatever method. As long as you have the entire tables correct, I'm fine with it. Okay? But this is my easiest way after 15 years of doing this thing. I've been designing FPGA for life. I do it for genomics and some stuff, but basically I'm a computer engineer. I study electrical engineering as well. So this is things I'm doing for life, really. Okay, so that's my own way how to interpret the things. Extremely easy, straightforward. No magic about it. Good? Okay. Now back to the midterm, or what we call sum of product. Is it clear how we calculate sum of product? Again, no magic. Just look at the output. Whenever we have one, take that midterm or them together. Done. Yes, please. Yeah, because no, forget about this. This is just something to try if we did the correct way or not. We were trying if the equation can replace the truth table or not. So your colleague, I don't know who picked that. Let's try the first row. It's up to you. You can try the third row. Let's try it together. We want A to be 1, B to be 0, right? So let's try it. Let's try it here. So A is 1, right? So we flipped it. It will be 0 times B is 0. So 0 plus A is 1 times 0, right? This is how we just try the third row with the equation. Now 0 times, this will be, yes, this will be 1 times 0 is 0. Excellent. Now 0 plus 0, 0. Does it match what we have in the third row? Is y 0 in that row? Yes. Now, any row, doesn't matter, although we pick this equation based only when y equals 1. Okay, but now the equation representing everything, the entire circuit. Doesn't matter which row you pick. If you try all these values, this y should be always true. Should be always exactly what you get from the equation. If you're not convinced, try it with the second row, fourth row. You'll see that. Is it clear? Not? All right, let me give you the new bar. Yeah, I have another new bar. I always like questions. So first you'll get the bar because you ask question. Let me know if this protein bar is better than the previous one or not. Okay. Yes, how we got the y. Okay. Is it clear how we calculate A, B, and y? Perfect. Is it clear how we calculate the midterms? Perfect. Now look at the y, which is the output. We look at the output, not the input. Look at the output. When exactly or where do we have ones? Second and fourth. Excellent. Now, whenever we have 1, pick the midterm. Whenever we have 1, pick the midterm. We have 2 ones, so we will pick this midterm, this one the second, and the last, because this is 1 also. And that's what we have in the equation. The second, A bar B, plus, sorry, if you don't see this side, I'm going to have it here for you. Yeah. A bar B, which is this guy, where we have 1, plus AB. That's the equation. So if I ask you, can you represent this circuit using sum of product Boolean equation? This is what you should provide as the final answer. Okay? Good? Okay. That's great. Now, another way to represent the equation, by saying this. What does this mean? Sum and then the index of the midterm. Because this midterm is not something unique to this question. Each of them is unique to the row, yes, but this midterm is not unique to this question. If I ask a totally different question, totally different y values, still you will have the same midterm. Because remember how we populate them? AB, 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 AB. Then whenever we have the input like 0, just add a bar, right? And this input, it always will be there. So we never rely on y. We always rely on the input. And the input will be the same for any kind of question. It doesn't matter. Whenever we have 2 input, you always get these 2 columns with the same value, right? So this minterm is not something unique to the question. Clear? So you can remember them if you don't want to understand how we calculate them. You can remember them. That should be fine for any kind of question. As long as you replace the a with whatever input we give you. For example, if it is x and y, then this should be x bar. Oops. What happened? It's weird. Okay. So this is sum. You know this icon, this symbol, represents summation, right? So sum, because we call it sum of product, sum of product. So sum, and then the index, this is 0. We start from 0. Always computer science starts with 0 because 0 is a number, okay? So 0, 1, 2, 3. So we pick the 1 and 3. So we just say summation of 1 and 3. Then I will understand what you mean by that. Summation of 1 and 3, okay? I could give you this equation, summation 1 and 3. This is the sum of product. Now build the truth table. You go backward. Okay? Any question? Sum of the indices of the minterm. Remember, this is 0, 1, 2, 3. So 1 and 3. Summation of this and this. All right. No question? Yes, please. Go ahead. Now you got bars for asking. Oh, you ask as well, right? I'm out of the new bars. Yeah, please hand it to your colleague, one for you, one for your colleague. Yes, please. Can I show? This machine is very noisy here. Can I show you how you get the answer in the exam? Yes, of course, of course. You do this for all subjects. Don't ask. Do this for everything in life. Whenever you calculate something, show me how you get it. You might make a simple mistake at the end. You should not get penalized for that. Okay? If you do everything correctly, done. You get the full grade. Okay. Always show me how you get the final answer. You got a bar? This is the last one. Okay. Yeah. No, I'll knock some heads. Please pass it. Yes, please. Go ahead. No, that will help you to cheat. You'll track your mind. You'll track your mind. Oh, I'm going to remember this question. Done. No, please ask me how we solve any question. This is how you should look for. Okay. Same as in logic gates when we study them. They were with 2 input. Now, oh, I have 4 inputs. What should I do with it? Okay. This is what I like about this subject. For example, XOR. Most of you remember the truth table for XOR, which is wrong. We should always remember how we generalize that. But I will have you covered. I have next maybe 6, 7 slides, all just examples. Okay. But I don't like this to think about it. Okay. Just use this question to practice. We can give you more material to help you. Okay. That's great. I can post 4, 5 questions to practice. Okay. Hopefully we could have recitation or lab for this course. Normally in all other universities we have lab for this course, honestly. It's good for some product? 100%? All right. Now you need to forget everything we studied so far. Forget sum of product. We're going to product of sum. But you'll see a lot of common things. Okay? Nice thing that we record the lecture. So now you can forget everything. You go back to the recording, remember. Okay? Now we call it product of sum. Product of sum. What does it mean? Product of something, right? So all of them are multiplied with each other. And each term is sum. So here we have dot because this is how it will be product of these three things. And each of them is sum. It means here we should have somewhere plus. Something like that. Okay? You remember what we have before? Sum of product. Sum of two things, and those two things are multiplied by each other. Products. Here we have the opposite. Product of sum. So each of them is sum. Okay? Now let's see the rules for that. All Boolean equation can be written as product of sum. So in the previous one, yes, all equation can be represented as sum of product. Likewise in here. We can use this method for all kind of circuit. As long as it's combinational, then it's done. Okay? Each row has a max term. Over there, each row has a min term, a unique min term. Over here, each row has a unique max term. Max term. Do you still remember the difference between min term and max term? If you ever get confused, what is max term? You don't care. What's the definition of max term? You care about the final answer. The final answer should look something like that. And to get this, you need each term to be with a plus sign or. And that's what you will have for each row. So these coming from rows of the truth table. And then you multiply them, not or them, as in here. In here, each row should get one of those terms, one of those things. This is how we got sum of product, right? So each row should be represented by something similar to this. But over here, each row should be represented by something like that. And that's what we call it as a max term. Okay? Each max term is false for that row. Each max term is false to that row. What does it mean? Over here, in the sum of product, we said the min term should be true, that row. Over here, the max term should be 0, or should be false for that row. Okay? Should be false. Let's see. We can have a truth table. Now, we will not build it again. Hopefully, it's clear to you how we build it. Okay? Now, we want to represent the third row. We want to build the max term for the third row. First, how many input? 2. A, B. Should we have dot or plus? Remember, what's the name of this method? No. Product of sum. So I'm going to multiply summation of things. So this should be add or multiply. If you're ever confused with min term, max term, all these things, forget about it. Just go back to the name of the form. The name of it, what does it say? Product of sum. So all of these should be summation. Okay? Now, we wanted this to be false, not true. We want it to be false. In the previous method, we want to calculate as true. Over here, we want to calculate as false. Sorry? Let's see how we want to make the third row 1 and 0. So this is 1 plus 0. What does it? No, first. What does it result? 1 plus 0 is 1, right? Oops, this is 1 and this is false. We want to have it as 0. What should we do? Excellent, excellent. You deserve another bar, but I don't have. So now, the 1 will be 0 plus this will be 0. We just got from the third row. We are not inventing anything, okay? 1 and 0. Now 0, 0 equals 0, and that's correct. And then we can use this to represent the third row. Okay? I don't know how to simplify it more. Hopefully everyone is following. Good. I know it's a heavy meal in the morning, but you need to practice. That's the only thing you should do. Just practice. Yes, please. Yes, 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 definitely, definitely. There is no magic behind it. Yeah, if you get the first quiz, hopefully there was no magic in that quiz. A little bit? Okay, maybe a little bit of magic. Yes, please. We will announce it, don't worry. But hopefully it will be, today is Wednesday. Let's say next Wednesday or so, because I didn't prepare the montage for the video. I want to have the quiz after I post the video on YouTube, so you can have time to review. Okay? Let's fix it to Wednesday from now, right? Please remind me, whoever missed, I think we have 4 students missed the quiz, the previous one. Please remind me to add more questions for you guys. Yes, please. For third row. For third row. Remember what it says? Each row has its own max term. Each row. Same as we did here, we are going to use the same method. Over here, we just populate, right? Let's populate for this. Now, this is what we got for the third row in the table. Now we want to build for all rows. How many input do we have in this table? 2. A and B. How many rows do we have? 4. Let's repeat it, populate it 4 times. A, B, A, B. Hopefully, guys, you can see. Okay. Now, this is sum of product or product of sum? Product of sum. So those should be sum. Okay? Just add plus. Right? Now, what should we do? Want to make sure all of them result in false. Okay? Based on those values. Let's try the first one, 0 and 0. How we make this false? Just leave it, right? It's already 0 plus 0 is 0. It's false. Done. That's correct. Okay? Can you synthesize? Can you compare over here? Can you see the pattern? Here, 2 bars. There, no bar. Okay, let's see the second. A plus B. 0, 1. We want the result to be 0. 0, 1. 0 plus 1 is 1. Wrong. We need to convert the ones to cancel out the ones. This is 1, so we should add bar over here. This is 1, we should add bar. These 2 ones, cancel them out. What is the pattern? Compare this with that. The opposite. Okay? Yes, please. All the time, because this is not based on the output. This is based on the input. It doesn't matter what's your equation, what's your circuit, what's your design. Doesn't matter. All the time you'll have the exact same value over here. All the time for any question. All the time you'll have these for any kind of question. We never look at the output. We just look at the input and try to come up with those max term as well as in min term. Got it? So if you don't want to know how we got it, just populate them. A times B, A times B, A times B, and then add the bars in this pattern. 2 bars, 1 bar, 1 bar, no bar. Over there is the opposite. Okay? Now we will look at the output. Only now. After we build the max term, we'll go to the output. Over here, we look at the ones in the output. Over here, we will look for the zeros in the output. Okay, let's see. This is 0, this is 0. We will take this, we will take that, and that's your Boolean equation. Good. Here we have product of sum. So we use this symbol to represent product, okay? And then the indices of those max terms. 0, 1, 2, 3. We have the 0 and the 2. So product of 0 and 2. If I show summation over here, what does it mean? Sum of product, okay? Sum of product. Here, product of sum. Is it clear? Now, when to use this, when to use that? Or why we have two methods? Why not just one? It's all based on those blue oval shape. Imagine the entire table, the entire y here is all zeros. How many times my equation will have terms? We'll have 4 of them, right? Imagine I will have single 0 and all ones. How many terms do I have in my equation? 1. Imagine I have 2 terms with 0, then I will have 2 terms over here in my equation, right? What's this telling you? Likewise, in here, we were looking for ones. To make the equation simple, as short as possible, as concise as possible, then if we want to use this method, we want to make sure that the ones in the output are less than the zeros in the output. If we want to use this method, we want to make sure the zeros in the output are less than the ones. Over here, it doesn't matter because 2 zeros, 2 ones. You can use any one you want. Okay? At the end of the day, it will be 2 things. This plus this, or this times this. But if I give you a question, and you have single 1 and 3 zeros in the output, which method you should choose? Here we are looking for ones. Over there, we are looking for zeros. If the number of ones are less than the number of zeros, use this. Your equation will be just one term. Only this one, for example, or this one. Yeah, if I didn't ask you for. Remember, those are a way to represent your circuit. Instead of sending to Intel or to any company a huge design with too many logic gates and so on, just give them the Boolean equation. Done. They know what your circuit should look like. Because I'm representing the functionality. Remember the definition of Boolean equation? I'm representing the functionality of the circuit. Right? Did we cover everything? Are you sure? Anything did we miss? Yeah, please practice. I emphasized this several times. The book has extremely nice resources for you. They have a lot of questions, as well as you have the solution manual, all posted by the author, okay? Just get the solution, get the book, all available for free online legally, okay? Just you need to set and spend some time. That's the only thing you need. You ask for more questions. Now you have too many questions at the end of the chapter. Just go read them. And you have the solution you can verify. Right? Good? Yeah, we can end it up here. We can continue with the some examples I prepared for you. So we can take them next lecture. Right? I'm going a bit slow, but hopefully this will give you more opportunity to think and ask questions. Okay? If you don't ask questions, I will jump into another topic and keep moving. So please stop me all the time, ask for more questions. Thank you so much, guys. Enjoy it. Today is rainy, so take care.